Alright, so this is day 2 of bit patterns. And again, I had Mr. Baronick's help creating these slides. So this is the question at the end of the last set of slides. What then are the largest numbers for these different sets of bits? Remember the equation was 2 to the n minus 1. So n is the number of bits. So if you have 16 bits, it's 2 to the 16th minus 1. If you put that into a calculator, that's 65,535, which is a pretty big number. Let's say you have 32 bits, then your number goes a lot higher. You have about 4 trillion. Or is that billion? I think that's billion. And then 64 bits is really big. 1.8 times 10 to the 19th. Scientific notation, perhaps. Okay, so it's a really large number. Would 16 bits be able to hold all the number of people who live in Portland area? I'd say the Portland area is about 2 million, so it wouldn't be big enough. How about Beaverton? It might be big enough, right? Certainly wouldn't be big enough to hold everyone in the United States. How about 32 bits? Is that large enough to hold everybody in the world? Where are we at population-wise right now? Yeah, 6 billion and climbing. 7 now? Yikes. 64-bit, yeah, you could hold everybody in the world. So just depends on how many bits you have. What are the largest numbers you can store? Okay, here's a number. It's in binary. Geez, how big is that number? Well, it's got lots of digits in it. And it's probably pretty big since we keep going to the left and there's another power of 2. But yeah, that's really hard for humans to read. Humans need a way to kind of shorthand to be able to understand binary. And what programmers do typically is instead of using base 2, they use something called base 16 or hexadecimal. And it allows you to avoid all the digits that you see up above. You can substitute one hexadecimal digit for each set of 4 binary digits. So you see this sometimes when you're working with computers. Say you're in web design and you want to set a color on maybe your titles, or maybe there's a paragraph. You want the text to be a certain color. The RGB values for red, green, and blue are usually written in hexadecimal. How do I know it's hexadecimal? The answer is some of the numbers are actually letters, so that kind of gives it away. If you like to know what your MAC address is on your network interface card, we'll learn about that. Each card has a unique number on it. It's like a serial number or a social security number. That network card's MAC address is usually written in hexadecimal as well. How do I know it's hexadecimal? Because some of the numbers are letters. Do you know your address? The network interface card has a unique address called the MAC address. To view the address, follow these steps. You choose Run from the Start menu, and then you type in Command. And then you type in this command called ipconfig all, and it'll show you what the physical address or the MAC address is. So I don't know if you can do that, but right-click here down on the window of your own setup and say Run. Yeah, and you want to type in CMD, which is already here. And that opens that black command window up. There's a lot of power in this window. A lot of people don't really explore it, but you can do some pretty powerful things just by typing text in here. Now, it used to be when I first started using PCs, there was no graphical interface. Mice didn't exist at that time. All you had was a keyboard. And the only way to interact with the computer really was through the keyboard. So it was not very efficient. But if you want to check out your physical or your MAC address, you say ipconfig, and then a /all. That's a /. And what you do is you'd use this to learn your IP address and lots of other stuff. It shows us our different network connections. We're connected to the Beaverton School District network. You can see the physical address. It's a series of 6 2-digit hexadecimal numbers. So you see hexadecimal there. If you're wondering what your IP address is, yours will be different. There's no two computers on the district network that have the same IP address. So minus 10.65.170.230. Here's the IP address of the router that gets us out to the internet. Here's the server that gives us our IP address. And then you see another number down here, which is, again, a lot of hexadecimal digits. Okay? So hexadecimal is used when you're trying to shorten a number so it's understandable, or at least a little bit more understandable than what you'd normally see. Okay, so when you're counting in base 16, okay, so we're going to learn how to count in hexadecimal. Now, there are a few things I need to point out about hexadecimal. Let me just bring up a text window. What mathematicians do when they have a base that's larger than 10, so we're counting, we start at 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, in hexadecimal, you still have a ways to go before you get to 15. So what mathematicians do is they say, okay, for bases larger than 10, we're going to start using letters. For 10, they use A. For 11 is B. 12 is C. 13 is D. 14 is E. 15 is F. And then, since you're in base 16, remember, whatever base you're in, you can't show that number, a single symbol for that number, so you have to put a 0 in and carry the 1. So 1 0 in base 16, well, is 16. Just like 1 0 in base 2 is 2. Counting in base 16 is kind of strange. I tend to try to memorize these letters, although I'm not very good at it. I know A is 10, I know F is 15. You know, 15 starts with the letter F. But I struggle with these interior ones. So I usually say A is 10 and then I count from there. So base 16 uses letters. Now the highest letter you're going to see is F. There is no G in base 16, but that's how you count. So now that we know that, I'd like you to, on your worksheet, fill out that last column. There's 3 columns to our worksheet. First column is base 10. The middle column you should have already finished. That's base 2. And now I'd like you to write in the values for base 16. So that's not too hard of a concept. But this affords you some ways of making binary numbers a little bit shorter and a little bit easier to compare. What we can do with hexadecimal, and we have our chart right on the front. For every 4 binary digits, you can substitute a hexadecimal digit. Using your form, you look on the binary column and you're trying to find 0001. And then look at your hexadecimal column and you see that 0001 in hex is just the number 1. Then you look at your binary column for 0010, which is 2, both in base 10 and base 16. So the base 16 number is 12. Notice I didn't say 12. 12 is in hex is different than 12. 12 implies base 10. 12 in base 16 is actually 18 because the 1 is in the 16 column. So you say 16 plus 2, that's 18. So don't say 12, say 12 when you're reading in hex. You'll note that the digits from 0 to 9 in hexadecimal and decimal are all the same. It's only when you get to 10 and any number higher do you start seeing letters come into play. So here's our next binary number, 1000, that's 8. And the second half of that byte is 0111. Look on our chart, that's 7. We substitute an 8 for the first 4 digits, and then we substitute 7 for the next 4 bits. Here's one that has a letter in it, this third one. So 1110, see we have an 8 and a 4, that's 12, plus 2 is 14. But we don't write 14 because we're doing this in hexadecimal, so we look at that pattern on our worksheet and we see that 1110 is equivalent to E in base 16. So we write the number E. Notice I didn't say the letter E. It's the number E. Next hexadecimal digit, we look at our chart and see the binary pattern 0101. find that same line in the hexadecimal column, and that's 5. So our hexadecimal number is E5. So what you can see though is that you can substitute a hex number for any 4-digit binary number. And what you get is the same number. If you translate either one of these to base 10, they would be the same number. So hexadecimal is a way of shortening a binary number. So it's a little bit easier to understand. Is it still easy to understand? Not really, because it's not base 10. That's what we're used to. But we can compare these numbers, like say, which is the largest number here? We can say, oh, I guess it's this one, E5. Because that's E and that's 14, so it'll be 14 times 16 plus 5. Yikes. It'd be a big number. Okay, so we did this the other day. We were trying to figure out this big monster number. I added one more column here. Remember, each of these have a place value, kind of like in base 10. Here's the 1's column. Here's the 2's. Multiply times 2, you get the 4's column. 8's column times 2 is 16's column. 32 times 2 is 64. Times 2 is 128. But anywhere you see a 1, multiply it times its place value and add it and put it over here on the side of the page. And then once you're done figuring all that out, just add them all together. And you see that this binary number, which has 8 digits, can be represented in base 10. And so what you get is 229. Now, that takes a long time to do. Look at that big mess. We just want to figure out what number this is. So what we do is before we convert it to base 10, we take the binary and convert it to hexadecimal first. Okay, so we take the first pattern, 1110, and we get E. Take the next part, 0101, which is 5, and we write E5. Now, because all we're doing there is substitution, we didn't have to do any math at all. And now, since we have only 2 digits, we only have to do 2 equations. The first column is the 1's column, 16 to the 0's column. So 5 times 1 is 5. Then E, which is 14, we multiply 14 times 16, and we get 224. Add those two together, and we get 229. Is that the same number as this one? Yeah, that's the same. Is that the same amount of math you have to do? The answer is no. This is a lot simpler. So the thing to take away here is if you have to convert a binary number to base 10, first convert it to hexadecimal just by substituting using your worksheet, and then go about doing the process of converting it to base 10. So here's the tip. If you have to convert a binary number to decimal by hand, first convert it to hex and then convert it to decimal. It's much easier. So substitute the hex and then convert the hex in base 10. So I'd like you to go out and get your MAC address and see if you can convert that into decimal. Remember, your MAC address is your physical address and it's written in hexadecimal. So you got to convert that address into decimal. On the calendar, there's this little helper thing, binary computer number systems examples, and it shows you how to do the conversion. The one we're trying to do is this one. So you write the 2 numbers in here, do the math, so that'd be 2 times 16 plus A, which is 10, times 1, gives you 32 plus 10, that would equal 42. So take each two-digit hexadecimal number and convert it into a decimal number or a base 10 number. But use this helper sheet to help you do that. Okay, so these are the main takeaways then from today's lecture. Computers are at their essence binary machines. Hexadecimal is just a shorthand form of representing binary numbers. So although we humans may use hex to describe values within a computer, computers don't think in hex or in decimal, but rather computers think in binary. So be glad that you don't have to think in binary because it's really hard to do. Luckily, the computer translates most everything from binary to decimal.